Ladies and gentlemen, good afternoon. Thank you for your introduction, and I would like also thank to Professor Wald for his nice and great overview of our industry. And I would like to continue in speaking about our new SBFEM method and our new software called Idea Connection. Uh, I would like not to speak about technical details and functionality of the software, but I would like to tell you something about our wonderful project. I would like simply tell you a story, uh, what we happened, what we went through in recent years. Our project started maybe 10 years ago with discussions over the beer with František Wald, and at the time we discussed if it is possible to do some more general design of connections, and in fact we started with the dream. And from this dream we came to current situation when we have new design method and when we have new software for using of this method. This 10 years ago we handled design of connections, and there were many cases, and you know it from your practice that there are many cases where you can design connection, but there is a lot of issues which you have to estimate. You have to use some tricky methods, and we were thinking about possibility how to resolve this issue. So we speak about all kinds of connections with open sections, with closed sections, with different positions of stiffeners, with openings in webs, in flanges, with shifted end plates, for instance, or combination of open sections and closed sections. We speak about stubs of this way, different gusset plates combined with connections with complex gusset plates for more connected members. We are speaking about anchoring and anchoring where you have more members connected to the base plate. All this stuff uh, was the source of our dreaming. Uh, Let me introduce me a little bit. My name is Sabatka. Maybe you don't know me, but I suppose that you know my software. I came in late 80s with my system to Nemeček-SIA, and you know this software as a Primavin. And then I was 10 years the development director in Nemeček-SIA, and at that time we founded SIA Engineer. But from 2009, I work in my own company, and we are focused to structural design, structural design of concrete, pre-stressed, also steel members and steel design. We cooperate with companies like Global, Midas, Interket, etc. So it was very short introduction, and back to connections. In our discussions, we think how to analyze steel joints in general and precise way. And it was really years of discussions, trials and errors, and but finally we tend to some possible solution. We collect information from engineers which handle practical design of connections. We work with university, especially with Prague University, with Professor Wald, but we got also information from outside of our structural engineering community. I will tell you something about aircraft industry later on. So we started with a dream. Then came several impulses. The first impulse was this one, this detail. One friend of mine came to me with this problem. This is the detail on the bottom cord of a truss girder. It was from one huge project of big car factory in our country. There were dozens of such girders. And when the factory was finished and they want to start produce cars, the investor mentioned this detail and then said it is a little bit suspicious. I do not believe that it is safe. So please prove it. So we made a model in C engineer at that time, and we make the linear analysis from plate or plate wall elements. We calculated, and everybody knows that even there was quite low stress. There were some peaks with stress maybe around 600 megapascals. And from these results, we were not able to really judge if this detail is okay or not. Everybody knows that the stress cannot be higher than yield strength, but the results are like that. So the first thing which we decide is that we cannot use this useless linear analysis, and when we want to handle properly with connections, we have to go to plastic analysis. These models you already saw in previous lecture. We use this ideal plastic material model with elastic part and plastic part. When we do this, it means that we cannot make checks of stress, because the stress is limited by yield stress. But Eurocode allows us to make the check against to strain, limit plastic strain, and this is recommended by 5% in Eurocode in this part of Eurocode. But there are discussions if this value is okay. Some professors recommend that it can be even higher, maybe 15%. But we think that with this 5 we are on good safe level. And when we apply this plastic analysis or elastic plastic analysis, then the results which we get are much more understandable, and we can see from them where is the real problem in the connection, and then we can do something with it. So now after 10 years, we are able to really calculate it, to really analyze this detail, and it was, the investor was right that it was really danger. There was danger place, and the design of this detail was not correct. It's true that at the time we propose for sure some stiffening of this this detail, so everything is okay. No crash had happened. Uh, but now we know what we should do, and for instance, even such small widener or hinge here can help a lot and decrease this elastic plastic strain. Or here, I'm not sure if you see it properly, but there are stiffeners in the direction of upper flange of this eye section, and these stiffeners solve the problem very nice. But there are a lot of different possibilities. In fact, if the designer do this analysis during his design, I think the best way is make this plate a little bit thicker, and then it's okay. So it was first thing, first impulse which said us that something we should do, because we had very powerful tools, but we cannot answer such simple question. Another one was this example. I call it the connection of president of Czech Steel Society. A friend of mine, he came to me again with his project. It was some building in Germany, and there were huge bracing diagonals. And he designed such diagonals in tension, and there were such connections. And he told me, I'm sure that these bolts are here for nothing. They will not take almost any force. So I would like to have something like that. And I want to save costs of these connections. Again, we were searching for tools for designing of this very simple things, and we did not find the proper solution. Now, of course, we can do it. This is analysis of this original solution and this new one, and you really see that the forces are really almost zero. So we can prove by analysis what everybody understands or knows. So this is this new solution, and it shows that this new CBFEM method is able to handle with the group of bolts of any topology. We speak about bolts. We in fact the bolt connection is no rocket science. It is two plates and several bolts. It's nothing special. But the analysis model needs some things. So at first we must be able to analyze this contact between two plates. And the plates in contact can work only in pressure, but not in tension. So you see, like here, there is opening between plates. And the bolts works only in tension, and we have to use a proper diagram which taken into account the plastification and other effects where the bolt is close to limit force. So as Professor Wald showed in his presentation, this is the right model of bolts. So we got several impulses and wanted to do something, and fortunately we got a nice opportunity. And the opportunity was the research project, which is partially sponsored by our government. And thanks to this project, we were able to put together quite nice research and development team composed from Prague University, from Brno University, and from our company. There are several key persons of this project, and it's quite huge project. The total investment is almost 1 million euro, and together there are more than 20 people which are somehow involved. And in this project we in this team we put together people with nice and long-term experience of component method, like Mr. Professor. There are people with excellent track record in designing of steel structures, and there are people with very good knowledge of finite element and software development. The name of this project, we call it Merlion, and maybe you know this is Merlion. Is this one? It's a symbol of Singapore. When we started, I was half year on Singapore, so I liked it. It is the synergy of lion and a fish. Yeah? So it is a little bit symbolic also for our new method. So this Merlion is now also symbol of our team. And when we set the goals in the beginning, it was clear from the start that we want to do the general method, which can be used for all joints, or we never can say all, but the very high majority of connections. But the method should be very simple and very fast, because if not, you will not use it. František Wald showed several models composed from finite elements, but these models are not for practice. If you model one bolt one day, you cannot do any project. So it must be simple and fast. And what is very important, we said that our method has to be comprehensible. It means that should provide really clear results. And the problem of a lot of design method is that you have some formula in code, and in fact, or very often you don't understand what is behind this formula. So this is not our intention. We want to show what's really happened in the connection. And we do also some validation in labs. This is the test of base plate in Brno University. We did not want to leave component method. We do not say that component method is wrong. It's a perfect method, a long experience, many tests. It gives safe designs of many connections. But we say that there is a weak point in the component method, and this is this model which is needed for calculation of internal forces and internal stresses in the connection. Yeah? In fact, for each topology of joint, you and somebody must derive this model. With this model, you calculate internal forces, and then you use specific checks for bolts, for welds, for each component. And this is the reason why this component method is not really general. It is suitable only for typical connections. And the simple decision was that instead of this we use finite elements, because finite elements are commonly accepted method. You calculate all structures with finite elements. So why not to use it for connections? There is only difference between building and connection is only difference in scale, but the logic is the same. And what is the our what we got is that we came with a new design method. František came with this name, component-based finite element model, CBFEM, and we say that it is a synergy of standard component method and finite element analysis. It's like this medallion was synergy of lion and fish, so we have synergy of components and finite elements. And this method is quite general. We can do stress analysis with this, but we can do also buckling analysis. We can investigate stiffness of connections, and we can provide quite comprehensible overall checks of connections. We had to came across a lot of problems during the research, and some things are quite unique, and we covered them by patent. Professor Wald already spoke about these verifications. I think you also saw this one. We made a lot of these studies, and and we compare new solution with existing ones. So we got this nice opportunity, but still, if you want to do something new, something remarkable, you need good people in the team, and these people should not know only these things like we spoke about, like component method and FEM analysis, but they must have a little bit advanced knowledge. The very important is this finite element solver. As we said, the using of FEM is quite common from, let's say, 90s. The first tries were in 80s of last century, and we can say that at that time the structural engineers were real pioneers in using of such advanced methods. We were far ahead of other industries, but in recent years, I think we're a little bit losing our speed, and mechanical engineers and for instance aircraft engineers are are doing more advanced models. We were lucky that in our team is a guy who came from aircraft industry. He worked for Boeing, calculated wings of Boeings, so they are quite safe. So it's good good for us. And what we did quite new. You know, softwares like Airstab and you know, when you want to connect two plates or plate and wall in your building, you have to resolve intersection between these two elements. And thanks to these intersections, very often the mesh is quite not nice. There are some tricky elements. This we completely do not do. We do the mesh on each plate separately. In fact, these meshes are not influenced. You see, like here on this part, this mesh much more dense than this one. And all connections or all connectors which we have in the connection, they are mostly welds and bolts. All these connectors are modeled with special interpolation constraints. They are like you can imagine small beams there, but they are not beams. It is really a force interpolation constraint. And with this these things we are able to move or to connect properly these separate elements. It is very nice for this meshing. You see that this meshes, if it is rectangular, then there are only rectangular elements. But everything is properly connected, and the advantage is that we have proper or precise forces in all connectors. We have precise forces in all welds, precise forces in all bolts. And what is side effect of this? When we do this, we have precise shapes of all plates, and we can use them for drawing. If you do it with intersection, then you do not have precise shape because there are thickness of these plates, and you have to add something to make the intersection. So we have in the team guy from aircraft industry. Another crucial thing was the modeling of this connection. We did not want to have a program like CAD program with drawings, but we also did not want to have 3D modelers like they use for car industry or such things. So we invented quite unique modeler for these steel joints, which is very simple for using, and thanks to this model, we are able to generate finite element model automatically without the influence or any effort of the user. We can use any cross sections, rolled, open, and hollow sections, welded, cold formed, very complex cross sections. We can have very general topology of connections. Can be 2D, 3D, anything you want. And this is again idea. We did not want to have the CAD program. We wanted to have program for engineers. So it means that all things which you do in the program, you do like when you do the connection in manufacturing process. So we we introduce so-called manufacturing operations, and when you construct the connection, you use cuts, you use stiffeners, you use haunches, ribs, end plates, shifted end plates, stops, splice connections, gusset plates for hollow sections, fin plates, cleats, openings, splice plates, base plates, and also some general operations. So this is also quite important thing. And what is important, we can have more connections in one joint, and they interact between each other, and we can analyze this interaction between each other. So when we had this project, we had people, we did the development. When I spoke about 10 years of discussions and then dreaming, the development was very short and fast. In fact, we got the first version of the program after 11 months of software development. And before we release it, we already start to work with engineers from the field. And at first we try to test user interface. Again, this interface is quite new. But we collect a group of pilot users, engineers, and we give them the software without any information, and ask them, please input your correction. And it was funny that this first group, at least one half of them were not able to do it. We have this navigator in the application where you go through from the top to the bottom, and we make the first version was very traditional. So at first we said to input project name and author and date and these things. Then you have some materials. Then you have cross sections and when they tested, most of them stopped in the third item and say, I don't know, I cannot continue. So we immediately rearrange it. We did it differently. Then we open it. You directly see your topology of the connection. From that moment, these problems disappeared completely, and we have no questions about that. So this is very important to test on people, not ourselves. There is another example. This is from new version. We did or we had a lot of comments to definition of welds. So we came now with such tool where you simply say it is fillet, double fillet, butt, and give the stiffness and give the thickness, and everything is much easier than before. So we released first version in last year in May in Prague, and then in fact we used Czech market, Czech engineers as a testing lab. Here I can say it. I cannot say them because they will be angry. But we really use them, and we in fact we use them as pilot testers. And what was very important, we collect all information from them. I visited all major design offices in our country, all influencers of this industry, and I collect a tremendous amount of pictures of connections, and then we generalize them and very fast improve our modeler. These pictures only show we started with the gusset connection to the gusset plate. It's very typical. It's nothing special, but then we from the people we got a lot of special things how to do it. This is from some bridge engineers. They wanted such openings at the end of these elements. This one, it's normal that you can weld the beam on the plate, or you can weld the beam or diagonal directly to the cord. But some people do it like that in fact use both options, welding to the plate and welding to the flange. Again, it was not in the first version. Now we have it. This one is quite nice to put between these two hollow sections. Put in fact such a rip. It stiff the flange quite nice and help these connections. And finally, we also have now the tube elements, circular hollow sections with all intersections. And when we start after this release, when we get the connections from outside, we realized it was quite disappointment at that time. We realized that maybe 30% of joints we are able to solve, but we collect all this and work maybe next 9 months, and now we think that 95% we can handle. And we realize again many other informations. One of them was that our original model of bolts in shear is not satisfactory. In fact we started with the mesh when we did not have the openings. We realized that we must model also these openings, and we develop also special like subsystem around this opening. You see this is a predefined mesh here, and in fact our bolt is only spring. It's one dimensional element, and we connect this point with these points at the edge of the hole and around the hole. There are these nonlinear constraints, interpolation constraints, and in this case there are also contact elements. Like we have contacts between plates, we have contacts between bolt and edge of the hole, and you see the results. And if the bolt is pressurized in this way, you see here is high stress. Here is almost nothing, and here we have this connection, this splice plates on the flanges. This one is, I think, from upper flange. This one is from bottom flange, and from this point of view, these bolts of shears, we call it like it's our masterpiece. That you see, like these bolts are acting in outside from the connection, and on the opposite side, where is the pressure, the bolts are acting in different sides of holes. So this we really, thanks to our lab lab tests, we improve this model very fast. And as I say, we tested a lot of examples on our engineers, and we collect the feedback and react on this feedback. One of them, or one of things which we realize that they are very important, is anchoring. Here you see it's not typical picture of anchoring, but it comes from users. I don't know what is it. This is some columns, many columns, and they do such things. This is the anchoring to the wall. It is thanks to this that we model also concrete block under the base plate. This block is not modeled by finite elements, but we use Winkler-Pasternak subsoil. It is the same like what you do when you design buildings, and in fact, in each point of the mesh on the base plate, we have some spring, which represent the stiffness of concrete block. We have contact elements between plate and between this concrete block. We have anchor bolts, again like this bolts in tension. The same we apply for anchor bolts, only the length is different and it behaves a little bit different. Very often engineers asked for mortar joints to take them into account during the check, so this was also added. And in this model we calculate contact stress between or under the base plate. Then we derive the effective area like in Eurocode, and calculate average stress on this effective area, and this is checked again against the concrete ultimate capacity. And we handle also with shear forces in base plates, and there are more options. Either we can, or you can consider that shear force is taken only by friction, or there can be shear iron, or the friction or the shear force can be taken by bolts, by bending of bolts. It is for this anchoring into the welds, into the walls. It is typical that only bolts that take this. So we got this feedback about anchoring, and for instance, this one is done again by some engineer. This, I think, it was from Poland, and in fact we did not expect to solve these things, but but this is the user find the way how to use our modeler to model this. In fact, this is the base plate. This plate is like a member, and on this member we have another member where the load is applied. It is a concrete wall, something like a small support, and on this there is another column. And it is developed by by users. We did not expect such things. So it was very positive feedback. Then were a lot of discussions about welds. To be honest, we little bit underestimated welds in the beginning, but now we improve this, especially from the point of view of understanding what is inside the bolt, inside the weld. I showed on the previous slide that there is no connection between two plates. These plates are a little bit separated. There is the thickness of this plate, and between this plate and this one, there are these interpolation constraints. Thanks to them, we can calculate precise forces in the weld, and now we present them like in these diagrams. There are forces in the direction of the of the weld. This is in this direction, and this is in direction of the welded plate. And if you want, you can use either the precise values of welds, or we can do averaging for the specific weld. And again, here is this new tool for handling with welds, which I already showed in user interface issues. We wanted to have our software very general for very sophisticated connections, but we want to keep it also very simple and fast for basic tasks and common connections. Therefore, we introduce templates. It means that when you create any connection in the software, then you can say save as template, and you can use this configuration for any other new project. I spoke about these manufacturing operations, and the template is in fact the sequence of these operations. Like at first you must have cut, then you weld end plate, then you define grid of bolts, and this sequence is saved. And then when you use it on new connection with different cross sections, with different angles, different topology, then these operations are done again, and so it works on quite also quite different situations, comparing with original connection. So for such topology, we can use directly predefined templates for different kind of connections. Like here, this is the fin plate. Here is the stub. I think this is welded. This is bolted with some haunches. This is bolted with one big haunch. So it means that for standard connections, you can use templates and be very fast and effective. And finally, we realized that with these standard manufacturing operations, that it is not enough for all this variety which you do in daily practice. These basic operations are very fast. You say shift it and plate, and it is directly done with stiffener and with all bolts, etc. But there is many cases which are not typical, and for this we introduce general operations, and you can use some general plate. It means you can put in any position in the connection, you can put plate of any shape. Then we have general cut of between two plates, or it can be a notch between two plates. The one plate is notched by another plate. This one was very very frequently asked, that people want to be sure that they weld it, that they weld two plates together, and want to have it under their control. And sorry, and then we have also group of bolts where you can define plates up to 5 plates which are bolted together with a group of bolts. And this general operations really enlarge the scope of solutions quite a lot. When we collect this information from the market, we got also bad examples of bad or not sufficient design of some connections and details. Maybe this is more interesting that good examples. What people appreciate is that even if they do bad design, we can show where is the problem and what happened. Yeah, this was the original design from one engineer, and another engineer which has to continue on the project said, I do not believe that it is okay. So we checked it with CBFEM method, and you see here that there is the plastification in the wall of this column, and in fact the wall collapsed thanks to this. And the strain was quite high. It's again, it's quite obvious this connection is not very very nice, but you can play with possibilities how to improve it, how to resolve it. For instance, here there is the bigger fin plate than before, maybe also thicker, and it was satisfactory. Or you can put a web doubler against this fin plate from opposite side. It stiff the web and problem disappeared. Or you can use the stiffeners. Again, you can see the influence of these additional plates, how they help the resistance in the connection. So it was one bad example. This is also quite nice. It is the joint in crossing of two diagonals, and these diagonals were from circular hollow sections, and the designer made it like that one diagonal is continuous, and he welded gusset plates to this tube, and the second diagonal was divided, and the welds were provided between tube and plate. This is again, we calculated, and you see that there are only green parts. It means that these parts, there is plastification, but not very high. It is less than this 5%. But if we show the deformation, you see that there is the ovalization of this circular tube, because this tube is not very stiff in this direction, and it means that from the point of view of stress, it's quite okay, but from the point of view of stiffness, you have bad solution. If it is bracing, it must be stiff, not like that. We compare it with another solution, what is normally done, that all diagonals are divided and welded to the plate. Then all this plastification is not here anymore, and you see that here we have deformation, and this is 10 times lower than this solution. In fact, for the same money, you have 10 times better solution. The stiffness is 10 times higher than this one. So it was another nice bad example. This one is again from Poland. One company contacted us and asked if we are able to solve this connection. It is from some tower mast, and there was the column. This plate was welded to the edge or the one leg of this. Maybe not to leg, but to this angle section, and this plate was bolted to the angle section. We modeled it, calculated, and it was quite disaster. Completely red, and deformations very huge, and so I was afraid that if it is really provide like that in reality. So I ask very if it is really your project. No, it's not our project. We got it from outside. We have to check it, and we think that it is not correct. So I said, okay, it's not correct. Perfect. We know that it is not correct. It is quite. Again, quite obvious. This if you see this display, there is diagonal with a huge normal force, and all this force should be taken by these three bolts, and it's not symmetrical. There is additional moment from these three, and this three on column are not able to take it. And you see it like here. There is the plastification, and this is the problem. So we make a simple or proposal that this plate is bigger. This connection is in fact this bolt is put also here. There are three plates which are bolted, but it's not a problem. And directly the situation in this plate is much better, and it's okay. So we like bad examples. If you have some, please send us. So this is some basic level of the design of connections, but we are not satisfied with basic level. We want to do something more, something extra. So we invented and implemented some more functions. One of them is how to analyze the resistance or design resistance or limit resistance of the joint. When you input your loads are in fact internal forces which are calculated in in your 3D program in internal forces in the frame, and you get the results like that. There is the problem, or it is green and there is not a problem. But we can do it in two ways. Either we can say apply all loads and calculate until the end, and this can be the result. So you see that connection is preloaded or load too much. Or we can say in somewhere in the setup that program should stop analysis when the limit is reached. Yeah. So then we apply the load and calculate until we get this 5% limit, and then we stop, and program tells you that we applied not 100% load, but only in this case 93%. And from this value, when you take this original and multiply by this, you know this limit resistance of the joint. So it can be used also for these studies. Then there is the issue of stiffness of connections. Only to remind, or the theoretical what is normally in codes is that stiffness is again bilinear. So we can analyze some initial stiffness. This is in this part. This is usually used in the global analysis of frame, or you can calculate the second stiffness for the specific level of loads. In CBFEM we calculate the second stiffness. So if you want to analyze the diagram of stiffness, you can simply add several load cases with different loads, and we provide the rotation and the stiffness for each load case, and we also classify if this connection is rigid, semi-rigid, or hinged. And when we do this, we can draw the diagrams of this evaluation or of this stiffness, and we got an idea to put together this diagram of stiffness, which is quite obvious, and also in fact the picture of situation in the connection. And we like this approach. František had, I think, two examples in his presentation. This one is the first one we made, and you see that we are here with 100 kilonewton meters, and there are first plastification around the bolt. And now we are on 150, and there is more plastification and starts plastification here. Again, 180 in web. There is now more development of plastic zones. Now we are in 220, and you see the web is plastified a lot. Then 250, and the plastification is now much faster. 260, the flange starts to plastify, and then you see that this branch is almost horizontal, so we add only small load, and the plastification goes very fast. So see this, and we are at the end because there is first area where we are over the limit. So This is we speak about this comprehensible results. This is one of them. You see what happened in the joint, and you can evaluate in fact safety of your design. If you if you are here and you see this, so you see where is the reserve. If you are here, it's quite dangerous, and that you can see that there is not much space to add another load. So from these pictures you can calculate the or you can see the design resistance. In fact, this is rotational capacity of the joint, and from the initial branch of the diagram, we can understand how is initial stiffness. So it was about stiffness, but buckling is nice issue in steel structures. Everybody of you is handling with members, with beams, with flexure buckling or lateral torsional buckling. The same problem, because we are still in steel. The same problem is in details. Yeah. What we do is that we have assumption that connected members cannot buckle. They cannot collapse due to buckling, because you made the proper design of these members, and they are designed against buckling. So if the design is proper, it cannot this effect cannot happen. And so we solve only local buckling inside the joint. And it can be for any topology of connections. There can be problem in gusset plates. Here is again some gusset plate, and here it is in the web of rectangular hollow section. So we solve only local effects, not global buckling of the frame. And you can see which information you can get and how they can help you. Like in this example, we have if corner, and you see here that the first buckling shape is on this this column web. Yeah. There are welded sections on rolled sections. This effect is not very dangerous. For thin plates in welded sections, it could be an issue. You see that there is the problem. So we put there the stiffener, and the first buckling shape moves to another place. And now it is here. And we also tells you this factor, which is the factor of critical load for this buckling. If you multiply your design load by this, then there is the effect of buckling. So this value is higher because there is the stiffener. So again we put stiffener here, and this disappeared, and the weaker part is now in the haunch. You see this collapse of flange of the haunch. It's, if you remember these pictures from lab on this first lecture, this is very similar. So for this we have this stability analysis. and we are tending to the end of our story. So we finally get to some solution. It's almost invisible. We, as I said at the beginning, we are focused to design of details and members of structures. We are not interested in finite element analysis. It is for that is very wide range of good programs on the market, like RFEM, like Axis VM, like Midas. We are not interested in CAD programs. Again, there is a lot of very good programs like Tekla, like Autodesk, Advanced Steel, or Revit. But our position is here that we do this proper advanced analysis of details, and we are linked with these programs. This link is done in this way, like on this example, we we are able to read the shape of the structure from a finite element program. But we do not calculate it. We have the shape and we have internal forces calculated by somebody else. In case of connections, we say I want to design the connection in this node, and from that we generate directly the model in idea connection, and you can make proper design of this node. This step is sometimes is not very easy because in your models very often not all members go really to one node. Yeah, sometimes you have some eccentricities, some rigid links, and but still these members are connected, so it cannot be done automatically, and you could decide which members you want to solve in one design of the joint. And with these CAD programs, we have in fact opposite way. This is example. Sorry for that. It's not almost visible. It is from Advanced Steel, from Autodesk. In this case, there is the precise model of the steel structure, precise model of the joint, and we read directly this model, and then we can make analysis of this. So these two ways of beam interface we can handle. And we are almost at the end. Finally, from this dream, we came to some achievements. I tried to explain on our story what we achieve and in which problems we have to resolve. So what we succeed or achieved is that we really made this verification and validation quite in very wide range and properly. We succeed with patenting of some crucial part of the system. We are a little bit pioneers also in this, because it's not very common to protect software tools or products by patent. So we protect some method which we use. Until now, we have more than 100 companies which are using our software in 8 countries. And what we like a lot is this feedback and the reaction of people, that we realized that they really do what we expect that they should do, or they follow our dreams. And we are sure or think that with this we can minimize the risk of defects in structures. In in many cases we can decrease the consumption of material in details and joints, and also we can significantly reduce the time you spend on your project. I spoke with one experienced engineer from Germany, and he told me that maybe 10 years ago in his company spent maybe 5% of project time on connections, and now thanks to new codes and new requirements, they spend maybe 35% on designing of connections. I don't know if it is true, if you have the same experience in your companies, but it was from one very good guy. He told me it. And we want to provide results in this way, that you really understand what's happened in the connection and how safe is your design. And now I have the last two pages. I don't know if all of you knows these terms which are there, like I don't think that you know what is cross method. I don't believe that all of you know what is Galerkin method. But when I when I finished the university in 80s, all these methods they taught us this methods. Three-moment equation was the method for continuous beam. Maybe some of them remember it. Cross method was the method for frames with fixed joints or nodes. Yeah, it's braced frames. Force method was special method for frames. Cremon diagram was the nice method. Yeah, definitely for this. Mr. Eiffel made Eiffel Tower with this, but you were able on a graphic way to calculate forces in these girders. Galerkin method was some for plates, I think. But there were many tasks for engineers which they have to simplify or estimate or maybe avoid the solution at all. So all these methods were available. They were very sophisticated, very good. But then finite element method appeared, and everything was gone in the history. Yeah, now nobody takes care about Galerkin method.